Hello, complex students. Today we're going to be talking about a variety of elementary functions. So this will include power functions and exponential functions with other bases besides e, and trigonometric functions, and hyperbolic functions, and inverse trigonometric functions. So all of the standard functions you would see in a calculus course, which you need in order to do things like integration theory. Anyway, let's go ahead and get started with power functions. So we're already somewhat familiar with power functions. So if you make a power function that has integral exponents, so things like, z to the third, or even something with a negative exponent like z to the negative fifth, these are already defined. It gets a little dicey though whenever we have power functions with rational exponents. So for example, z to the 1/2, or whatever, z to the negative 3/4. We do have a definition for these, but we've seen that they become multivalued. For example, we know that when you take square roots, you always get 2 square roots, and so we have to pick one of the roots that we want to focus on. A typical thing is to choose the principal root. If we're looking at a root multifunction, we can pick the principal root to get a single-valued function. But then, what would we do with something like if we wanted to do z to the square root of 2 or z to the negative pi? So we can't define those in terms of roots or just, basic multiplication facts. The trick is to use an identity that we saw. We saw that z to the n can be expressed as e to the n times log z. Now, log z is a multifunction, so this is a multifunction. This identity that we had here was true for n in the integers, but it provides a motivation for giving the following definition. So if we want to replace that exponent in z to the n with just some other, just any old complex number, the way we'll do it is like this at the bottom. So for non-zero base and any complex number c, z to the c is defined to be e to the c log z. You notice that we could even, in this definition, we could even have z to the, a complex number exponent, something like z to the I plus 2 or something like that. We could make sense of that using this definition. So the first thing to notice if we start examining properties of general power functions is that z to the c, because it's equal to e to the c log z, it's a multifunction or a multivalued function. So for example, let's look at the function f of z equals z to the I. And then I could think about, well, what's the value of f of I? So f of I would be I to the I, which is equal to e to the I log I, according to our definition in yellow above. And then we can write out what that means. So that's e to the I, and then log I, just real quick, remember I, you can write it in an exponential form. Its radius is 1, and its and its angle is pi over 2. So its principal argument is pi over 2. So I can write e to this log I as, it's natural log of the radius, which is 1, plus I times the argument, which is pi over 2, plus 2 pi n, where n is any integer. And then upon simplifying that a bit, we know natural log of 1 is equal to 0, and then actually end up multiplying an I times an I here, and getting a negative 1, so you end up with e to the negative, I guess you could pull a pi out there if you wanted to, e to the negative pi times 1/2 plus 2n. So notice this is just a real number each time. Kind of funny it works out that way, but I raised to the I is always a real number. But it can be lots of different real numbers because n here is an integer. We could do the principal value of it. Principal value of I to the I would be equal to e to the negative pi over 2. But the point is, right here, lots of values, right? So these power functions are multivalued. And so we have to think about that. If we start thinking about wanting to do differentiability or things like that, we got to restrict to a branch, just like we did with logarithms. One property that we can expect is that when you do 1 over z to the c, you're hoping that would just be z to the negative c. And it is, because when you look at the definition of things, 1 over z to the c is 1 over e to the c log z. But we already have this property for the exponential function, e to the whatever. We already know that e to the negative z is 1 over e to the z from a previous discussion. So I can write this as e to the negative c log z, which of course is the same thing as z to the negative c. So we do have this identity that we would hope to have. So if you pick a branch of that logarithm that's in the exponent of the power function, let me highlight that just for emphasis here. So if you're looking at the power function z to the c, you can focus on a particular branch of the logarithm that's in the exponent, and that'll give you a branch of the power function. And when you do that, the function becomes single valued, and also by virtue of the way it's defined, it's e to a power, it's going to be analytic, and you can compute the derivative, and it turns out to be exactly what you would hope it would be. So the derivative of z to the c obeys the power rule. It'll be c times z to the c minus 1, where c is any complex number there, right? So that's pretty cool. I suppose we should see why that's true, how that works out. Well, it's just going to fall back on using properties that we already know about the exponential and logarithms. So if you take the derivative of z with respect to z of z to the c, then that's the same as the derivative of e to the c log z. But we already know from before that the derivative with respect to z of e to the z is e to the z. So we can apply that along with the chain rule here. Now, we're restricting to a single branch of the logarithm. It doesn't matter what branch, but we know from before that if we restrict a logarithm to a branch, we can compute the derivative of the logarithm as well. And the derivative of the logarithm restricted to a branch is 1 over z. It doesn't matter what, again, doesn't matter what branch you use. So we can use those facts from before to compute this derivative above, and you'd get e to the c log z, because the derivative of e to the z is e to the z, but then you got to multiply times the derivative of the inside function using the chain rule. So you'd then multiply times the derivative with respect to z of c log z. Then we can use the linearity property to pull the c out of the way. So we get e to the c log z times c times 1 over z. So we can write the 1 over z as 1 over e to the log z, like this. That's just using an identity that we knew from before. So I'm going to pull the c out to the front, and then we've got e to the c log z minus log z. So that's c e to the c times, well, I guess we could just factor the log z out and write it as c minus 1 log z. And then, yeah, that's what we have left here is actually just by definition z to the c minus 1. So we get c times z to the c minus 1. So that verifies the power rule works for any complex numbered exponent. So, of course, we had to pick a branch of the logarithm to make z to the c a single valued function, so we could talk about derivatives and all that good stuff. And if we pick the principal branch of the logarithm, then we get the principal value of the power function. So z to the c will just be e to the c times the principal branch of the logarithm of z. And also, we sometimes speak of we talk about the principal value of z to the c, I think, when we're thinking more about a specific value, like if I plug in a particular number for z. But then we can talk about the principal branch of the multifunction z to the c, and it's the same definition as the principal value, just a slightly different point of view, and you're thinking of it more as a function rather than a particular number. So f of z is, get the principal branch here, you just do e to the c times the principal branch of the logarithm as well. I guess the principal value and the principal branch are sort of synonymous. Now it also makes sense to now define an exponential function with base c, where c is any complex number, to be e to the z log c. And again, this function would be multivalued just because the logarithm up there in the exponent, can have lots of different values. But once we specify a value for that logarithm up there in the exponent, then this becomes a single-valued function because e to the z is single-valued by its definition. And it'll end up being entire because e to the z is differentiable everywhere. So your function c to the z will be entire after you picked a specific value of the logarithm, and you get the derivative formula is this. You get log c times c to the z is your derivative. So it's just like back in calculus class. It's the same derivative. And, to get from here to here, all you're doing is just applying what you know about the derivative of e to the z is e to the z. And then it's times a constant in the numerator, so you just use the chain rule and you end up with a multiple of that constant. So nothing tricky about how to get that derivative there. So let's look at a few examples of some of these power functions, and just have some concrete examples to make sure we understand how the definitions work. So -1 to the 1 over pi. According to our definitions, -1 to the 1 over pi would be e. Then you have 1 over pi times log of -1. Log of -1 has multiple values, so you can write those out like this. This would be e to the 1 over pi. And then log of -1, well, you do natural log of the natural log of the modulus of that number plus I times the arg of that number, so arg of -1 plus 2 pi n. The arg of -1 is pi, so this comes out to e to the 1 over pi. The natural log of absolute -1 is 0, so you have 1 over pi, and then you have I times, and then arg of -1 is pi plus 2 pi n. Notice that you can pull a pi out and then cancel with the 1 over pi, so this becomes e to the I times 1 plus 2n. And then the principal value of this thing is just going to be where n is equal to 0, because when n is equal to 0 and the expression for the logarithm at the top, that's how you get the principal logarithm. So if you just put in n equals 0, you get -1 to the 1 over pi ends up being e to the I. Okay, z to the 2/3. Now, this is a power function with a rational exponent, so we could interpret this as just the third roots of z squared, but let's do it according to this newer fangled way of doing things. So according to our definitions, this would be e to the 2/3 log z, and then we can write out what the log z is. That's e to the 2/3, and log z you can write as natural log absolute z plus I times the argument of z, the principal argument of z, plus 2 pi n, where n is an integer. And so if you want to take the principal value of this, you would just put in n equals 0. And so the principal value of z to the 2/3 is e to the 2/3 natural log absolute z plus I times just arg z. And if you want to break this down a little bit, you can. So you could write this as e to the 2/3 natural log absolute z times e to the I arg z. Oh, there's 2/3 there, I forgot. 2/3 I arg z. And this coefficient here, that's a real number. If you want to put this into sort of a polar form, modulus of z is your r. And so you could think of this as r to the 2/3 if you wanted to. I think I'll just leave it as mod z though. So you end up with the third root of mod z squared, and then the e to the 2/3 times I times arg z. You can put that into cosine and sines if you want to, so you can write that as cosine of 2 arg z over 3 plus I times sine 2 arg z over 3. Then there would be that principal value, or the principal branch of z to the 2/3. If you want, you could think about this exponential function with a base other than I. But, the standard way to do this would just be to convert it to something with a base of e. So if we just apply the definition of the exponential function with base I, then I to the z would be e to the z log I. And that's a multifunction because log I has many values. You could write out what log I is. So you do natural log modulus I plus I times the arg of I, which is pi over 2, plus 2 pi n. And then if you substitute n equals 0 into the previous expression, which is, for all integers z, then you would get the principal value of I to the z. So I to the z, principal value would be e to the z. Of course, natural log of modulus I, that's just a 0, right? So you end up with e to the z, and then you got just I times pi over 2. So I pi over 2. And that's just e to the z times a constant, right? So no big deal. I mean, you can differentiate it, find values of it, all that good stuff. So this is a pretty simple function. Because these power functions and these exponential functions with other bases, because they're multi-valued, you get into some weirdness if you try to start, thinking that all the, familiar exponent rules are going to just work for you. Like a familiar exponent rule for real numbers is that whenever you do, something like a times b and you raise it to a power of x, you get a to the x times b to the x. But we don't necessarily get that here because there's 3 expressions involved in this equation, and depends on a choice of branch to get each of those 3 values in that equation. And so if you try to just pick one branch, it may not work for all 3 terms. We saw something like this with logarithms too, right? So this isn't surprising, but just as an example to drive the point home, here we have 3 chosen complex numbers. Z1 is 1 plus I, Z2 is 1 minus I, and Z3 is negative 1 minus I. So it turns out that if you do Z1 times Z2 to the I, and then you take the principal value of it, that would be equal to like distributing the I exponent over those 2 terms, as long as when you're choosing principal values. So it turns out that this little equation is true. And you can verify it just by, computing each side, right? So if you do Z1 times Z2, and then you raise it to the I first. So first multiply Z1 times Z2. Well, you can see that Z1 times Z2 works out to be 2. So it's just 2 to the I. And so then the principal value would be e to the I, and then you do log, the principal log. Do e to the I times the principal log of 2, which you can work out a little bit. That's e to the I natural log of modulus of 2, which is 2, and then plus I times the argument, which is 0. So what do you end up with? Just e to the I log 2. E to the I natural log of 2. That's what you end up with. And then you can do, on the right-hand side, okay, next we'll do Z1 to the I. So that's 1 plus I raised to the I. And then we need to do the principal value of that. So principal value of that is e to the I, and then you do the principal logarithm of 1 plus I, which is e to the I. And then you take natural log of the modulus of that number, so that's natural log of square root of 2. And then the angle is pi over 4, so you get I times pi over 4. Then Z2 to the I, that's 1 minus I to the I, taking the principal value of 1 minus I to the I. You get e to the I principal log of 1 minus I, which works out to be e to the I natural log square root of 2, and then you just get you get the angles negative pi over 4 here, so you get minus I times pi over 4. And then you can take those last 2 expressions and multiply them together and see what you get. But it's kind of clear that when you multiply those 2 exponentials and add their exponents, you're going to get a negative pi over 4 and a positive pi over 4 to cancel and give you zeros on those parts. And so what you see is when you do Z1 to the I, well, when you do principal value, Z1 to the I multiplied times principal value of Z2 to the I, you end up with e, and then the pi over 4's cancel. And on those natural logs of square root of 2, you can pull 1/2 down. So you're going to get 2 times I times natural log of square root of 2, but then you can pull the 1/2 down and cancel the 2's off. So you just end up with e to the I natural log of 2 again. So just, add those exponents there. You can see how it cancels off if you like add those two exponents together there and see if you don't get I times natural log of 2. On the other hand, it's not true that when you do z2, z3, and you raise that to the I and you take the principal value of it, that you get the product of the principal values of z2 to the I multiplied times z3 to the I. And you could verify it's the same way. Just check both sides separately. So if you do z2, z3, and you raise that to the I, well, what is z2 times z3? z2 times z3, you're going to get negative 2. So you do negative 2 to the I, and let's see what happens here. So you do negative 2 to the I, and you want to take the principal value of it. Then you're going to get e to the I. This time you're going to do a principal logarithm of negative 2, and you're going to get, like, the angle for negative 2 is pi when you take the principal argument of it. So you end up with I, and then you still have natural log of 2, because that's the modulus is 2. So I times natural log of 2 plus I times negative pi is your angle. So let's see, what do you end up with if you sort of simplify this down a bit? Well, you see when you distribute that I, you're going to end up with a e to the, the angle on the logarithm there is not negative pi, it's positive pi. So anyway, that'll simplify down to when you distribute the I around, you get e to the negative pi times e to the I natural log of 2. Let's just recall, principal value of z2 to the I is equal to, what do we get up there? E to the I times natural log squared of 2 minus I pi over 4. And then also we can get the principal value of z3 to the I. The only difference in the computation is just what the angle is when you do the principal logarithm. We can see that z3 though is a third quadrant point, and so we're going to get negative 3 pi over 4 for its angle. So you end up with e to the I natural log squared of 2 minus I times 3 pi over 4. And then just multiply those last two expressions together. And when you add those exponents together there, you're going to get e to the I natural log of 2, and then those angles. And remembering that you distribute this I here, those negatives are going to become positives, and so then you end up with e to the positive pi. And then you can see, these things are, they don't have the same angle, so they're not equal here. All right, next we'll talk about defining the trigonometric functions. This is a good time to sort of motivate where this Eulers formula comes from. So remember Eulers formula. Eulers formula says e to the ix, where x is a real number, is cosine x plus I sine of x. I think it would be a good time to talk about where that comes from. I mean, it seems like an odd thing to just say e to the ix equals cosine x plus I sine x, but there's a good reason for using that exponential notation there. First of all, I want to remind you of a few facts from calculus class. So we have Taylor series expansions for e to the x, sine x, and cosine x. So e to the x can be written as 1 plus x squared, and plus so on, where you're doing x to the n over n factorial in the sum. So you can write this as sum n equals 0 to infinity of x to the n over n factorial. And sine of x is kind of like, you can see there's some relationship between sine of x and e to the x. It's like sine of x is the odd degreed terms from the e to the x formula, but then the sign is alternating. And cosine of x also looks like it has a relationship to e to the x. If you just look at the even index terms in e to the x and then let the sign alternate, you get the cosine. So check out what happens when you take the Taylor series for e to the x and then substitute I times x in place of x. So you'd get 1 plus ix plus, then you'd have ix squared over 2 factorial plus ix cubed over 3 factorial. Maybe I'll just carry out a few of these terms. Ix to the 4th over 4 factorial, ix to the 5th over 5 factorial, and so on, okay? And then you look at what happens. So using what we know about powers of I, like I squared is -1, I cubed is -I to the fourth is +1, and so on, we can write this as 1 plus ix plus, then it'll be minus x squared over 2 factorial. Then it'll be a minus x cubed over minus I times x cubed over 3 factorial. Then you'd have a plus x to the fourth over 4 factorial. And plus I times x to the fifth over 5 factorial. And if you analyze what's going on, the odd degree terms here in yellow, you can kind of see a pattern to it. And similarly, you can see a pattern going on with the even index terms. So if you just sort of group all the green terms together, which you can do because you have absolute convergence and these sort of things that allow you to get away with it, you can write this as 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And then, of course, the next term after that would be x to the sixth over 6 factorial. Be a minus, though. And so on. And then group the yellow terms together and factor an I out of them. So you factor the I off, and you get x minus x cubed over 3 factorial plus x to the fifth over 5 factorial and minus x to the 7 over 7 factorial, and so on. Of course, that works out to be exactly cosine x when you think about the Taylor series above at the top there. And then you get plus I, and then you have the power series for sine of x there. So it wasn't just a notational convenience that we said e to the ix is cosine x plus I sine x. It really is that when you look at the Taylor series expansions. I always thought that was kind of cool how that worked out like that. Now what we want to do is sort of expand Eulers formula to not just to do e to the I times x, where x is a real number, but we want to get it to where we can do e to the I times z, basically. We want like an Eulers formula for that. And this will also, give us some motivation for how we define sine of z and cosine z. So here's how we're going to define sine of z and cosine z. Well, when we use Eulers formula, so there's Eulers formula, the first thing I'm underlining here. But also, if you put in sort of negative x, like you do e to the negative ix, you end up with the second formula here. And that's just because cosine of negative x equals cosine of x, and then sine of negative x equals negative sine of x. So you pick up the negative in the middle there. And then when you add those two expressions together, e to the ix plus e to the negative ix, you can see that the sines cancel and you get 2 times cosine. Then you can solve for cosine of x, and you'd get cosine of x turns out to be e to the ix plus e to the negative ix divided by 2. And similarly, if you subtract those two equations that I've got underlined in blue, you see that the cosines will cancel out, and you end up with 2i sine. And then you could divide both sides by 2i, and you find that sine of x equals e to the ix minus e to the negative ix divided by 2 times I. And because of these two sort of identities that are true whenever you've got x in there, like a real number x, it motivates us to define cosine of z to just be e to the I times z plus e to the negative iz over 2, where here z is any complex number. And similarly, we're going to just define sine of z to be e to the iz minus e to the negative iz over 2i. So this is how we define the trigonometric, functions, or at least sine and cosine, of a complex number. We're defining it in such a way that it aligns with the real number definition of sine and cosine, the things we have encircled in blue there. That's true for any real number. So these ones that I've got highlighted in yellow are going to be true when you plug in a real number as well, but they just expand the definition of sine and cosine to complex numbers. And one thing you notice immediately about this is that because e to the iz and e to the negative iz are entire functions, means differentiable everywhere, then immediately you get sine and cosine are entire. So sine and cosine are very good functions, differentiable everywhere. And they're not multivalued. These are single-valued functions. And then, of course, what do you hope the derivative of sine is? Of course, it's going to work out to be cosine of z. And the derivative of cosine of z is going to be negative sine z, just like it always was for real numbers. So we could verify, one of these derivative forms. Once you see how to, verify one of them, you see how to do the other one. So like, let's say I want to do the derivative of sine of z. Well, I'll just write down the definition of sine of z. E to the I z, get the minus in the middle on that one, minus e to the negative I z divided by 2 times I. And then, just use the chain rule and rules of differentiation that you know the derivative of e to the z is e to the z, so we're going to make heavy use of that. So you can pull the 1 over 2i out as a scalar multiple, and then the derivative of e to the iz is I e to the iz, and the derivative of e to the negative iz is, you pull the negative I down, you end up with positive I e to the iz, and then you can bring that I out and cancel it with the one in the denominator there, and you end up with 1/2 e to the iz plus e to the negative I, it should be a negative there, negative iz, and that's just cosine of z, as advertised. And doing the derivative formula for cosine of z is just about as easy, so I'd encourage you to check that the derivative of cosine is negative sine of z. And we have a whole bunch of trigonometric identities that can all be verified very quickly just using what we know about exponential functions and our new definition for sine of z and cosine of z. So we've got these negative angle identities at the beginning. Sine of negative z equals negative sine of z, and cosine of negative z equals positive cosine of z, just like before. So all of the identities that I'm going to show you here are basically things that we already knew, or just like what you would have had in calculus, or in previous trigonometry courses. E to the iz works out to be cosine z plus I sine z. So now we know that Eulers formula works not just for real number like e to the ix, but it works for e to the iz, and you get the same formula. We've got sum of angles identities just like we always had. So sine of z1 plus z2 would be sine of z1 cosine z2 plus sine of z2 cosine z1. And you have the familiar sum of angles, or sum of complex numbers now, identity for cosine. It'd be cosine z1 cosine z2, then minus sine z1 sine z2. We got double angle identities. So sine of 2z, you can write that as 2 sine z cosine z. And cosine of 2z works out to be cosine squared of z minus sine squared of z. By the way, you get both of these identities just from the sum of angles identities, right? Like sine of 2z, you can think of that as z plus z, and then just use the sum of angles identity. So you get, these give rise to these. Let's see, I think these are called cofunction identities back in trigonometry class. Yeah, I think these are called the cofunction identities for sine and cosine here. Sine of z plus pi over 2 is cosine of z, and sine of z minus pi over 2 is negative cosine z. Especially that the first one of these two identities are the reason that it's called sine and cosine. It's the co part because of complementary. And anyway, you can derive both of these identities from the sum of angles identity too. You get the Pythagorean identity. Sine squared plus cosine squared of z equals 1, as always. And then, of course, both sine and cosine have a period of 2 pi, it turns out. So sine of z plus 2 pi is going to work out to be sine of z, and cosine of z plus 2 pi is going to be cosine of z. So that just points out the period of sine and cosine. If you do just add pi, it's kind of like you're going, if you think back just to like the unit circle, right? If you add pi to an angle, you're going to be on the opposite side of the circle. So you're going to get negative sine of z and negative cosine of z for both of these, where you do z plus pi. But again, all these identities down here would stem from the sum of angles identities for sine and cosine. And so once you verify the sum of angles identity for sine and cosine, which is not hard to do, using the definitions and what you know about exponential functions, you quickly get all these other sort of standard identities that we've always had in trig. There's some new identities too that start to reveal some fundamental relationships between hyperbolic functions and trigonometric functions that previously wouldn't have been able to see, just when we would be restricted to real numbers. So a couple of definitions that you may or may not have seen before involve hyperbolic sine and hyperbolic cosine. So sometimes people cover this in calculus class and sometimes they don't. But the hyperbolic sine function, so sometimes we call it sinh, S-I-N-H. Sinh of y is e to the y minus e to the negative y over 2. And then there's a hyperbolic cosine, or cosh. Cosh of y is e to the y plus e to the negative y over 2. Notice how familiar similar this looks to how we define sine of z and cosine of z. It's like the same formulas, but without the i's and the exponents. Now check out what happens whenever you take the old real valued versions for sine, the hyperbolic sine and hyperbolic cosine, but then substitute iy in there in place of y and see what happens. So sine of iy, let me just write down, remember sine of z is e to the iz minus e to the negative iz over 2I, okay? So I want to plug iy in for z into that. And when you do that, you get e to the I times iy minus e to the negative I times iy, and then that would all be over 2I. So what do you get? How does that simplify out? Well, the i's, you multiply together and you get e to the negative y minus e to the positive y over 2I. But one thing to remind you of, 1 over I, you can write that as negative I. So using 1 over I equals negative I can write that expression as, well, you can see that I'd get an I in the numerator, so it'd be I, and then the term, because of the negative, I could change the order of the terms in the top, and you'd get e to the y minus e to the negative y over 2, so that's I times sinh y, and what we have at the top in green there. And we can do a similar thing with, if we do cosine of y, remember cosine of z is e to the iz plus e to the negative iz just over 2. So we plug iz in place of z here, and you end up with e to the I times iy plus e to the I, negative I times iy all over 2. And you end up with e to the negative y plus e to the y over 2. Well, that's the same as cosh y, the second formula up at the top in green. So summarizing that here, you see that sine of iy equals I sinh y, and cosine of iy equals just cosh y. And now we can use this to do something kind of cool. If you put z into the form x plus iy, then it turns out you can break up sine of z in the following form. Sine of z can be written as sine x cosh y plus I times cosh x sinh y. I forgot my I there. Plus I times cos x sinh y. And cosine of z can be broken up as cosine z, or cosine x, cosh y, plus I times sine of x sinh y. What we have here is, this breaks sine of z and cosine of z up into its component functions, like the u and the v that we use like when we do Cauchy-Riemann and things like that. So that's an important way to be able to break up your sine and your cosine functions. And this is something I'll have you verify in your homework, these two identities here. But it'll make use of what we just discovered here about sine of iy. It's going to come down to something along the lines of, e to the iz. You can write that as e to the I times x plus iy. And then, breaking things up into your components, you're going to get some sines and cosines of iy that you take advantage of, and then you want to take advantage of these formulas here. Okay. One thing that's kind of nice from these last two identities, we can actually get an expression for the modulus of sine of z and the modulus of cosine of z squared. So just square it to get rid of the square roots that you get whenever you do moduli. But the modulus of sine of z can be written as sine squared of x plus sinh squared of y. And for cosine, the modulus of cosine of z works out to be cosine squared of x plus sinh squared of y. So one thing that you can observe right away is that unlike the real valued version of sine and cosine, the complex valued sine and cosine functions are unbounded, because when you look at these terms, the sinh function, as y grows large, the sinh of y goes to infinity, because it's got that exponential term. I mean, if you look up here in green on the left up there, the e to the y term would go to infinity, the other term would go to 0. If you put in a complex number into the sine or the cosine that has a large y component, then it's going to have a large modulus. So these are unbounded functions. We can't say things like, for real valued sine and cosine, they're bounded between -1 and +1, right? But that's not true for complex numbers. So that's a difference. And here's a theorem that just tells us where to expect the zeros and the singularities of trig functions. Well, the first one just has to do with zeros of sine and cosine. Well, we'll talk about singularities of the other trig functions like tangent and cotangent shortly. This theorem says that sine of z equals 0 if and only if z is a multiple of pi, just like with the real numbers. And cosine of z is equal to 0 if and only if z is, take pi over 2 and then add multiples of pi to that. And that's also just like with the real numbered versions of sine and cosine functions. So let's see how this works. It's an if and only if. One direction's easy. The reverse direction, well, we'll get to that soon enough. Let's do the hard direction first. So start by supposing sine of z equals 0. And I'll do this for the sine part of this theorem, part 1 of this theorem, and then, of course, the proof for the cosine part would be very similar. So start by supposing sine of z equals 0. Then we want to argue what z has to be. We want to argue z has to be n times pi. So then we can say we have modulus of sine z squared must be 0. And we had this nice formula for the modulus of sine z squared in terms of these hyperbolic functions. That tells us that we've got sine squared of x plus sinh squared of y has to equal 0. Here, z is x plus iy. These are both squared terms, right? So when you square, and we're talking about real numbers here. So the square of a real number is always going to be non-negative. So the only way that this sum of non-negative things comes out to be 0 is if both of the terms are equal to 0. So this tells me that sine of x must be 0. And we know that the sinh of y has to equal 0. From that first equation, we're talking about real numbers here. We can see that the only way that sine of x is equal to 0, this is just what we know from calculus. X has to be some multiple of pi. And the only way sinh of y is going to be equal to 0, just over here to the side somewhere, e to the sinh of y is e to the y minus e to the negative y over 2. The only way that that's going to be equal to 0 is if that numerator is equal to 0. And the only way that's going to be equal to 0 is if e to the y equals e to the negative y. And the only time that happens is exactly when y is equal to 0. So we see that x has to be a multiple of n pi and y has to be 0. So that tells me what z is equal to. So z is equal to n times pi plus, I times 0 if you want. So that's just n times pi. And of course here n was an integer. So that proves the forward direction of this thing. And then the reverse direction is just evident because sine of z agrees with the real valued version of sine whenever you plug in a real number. So if you suppose z is the real number here, n times pi, yeah, of course sine of z is going to equal to 0 at those points because sine of z has the same value as the regular old sine function. If you want to prove the second part, the easy way to go about it, I suppose you could do it from scratch and just do it similar to the way we did above. Or you could just convert it to the, cosine of z is negative sine of z minus pi over 2, and then just use the first result. It's a little easier. And we can go ahead and define the other 4 trig functions in the way that we always do. So we have a sine of z and a cosine of z, and good differentiation facts. We know where it's equal to 0, all that good stuff. So sine of z is just going to be, tangent of z is going to be sine of z divided by cosine of z, as it always was. Cotangent will be cosine z over sine z. The secant z is 1 over cosine z, and cosecant z is 1 over sine z. So let's focus on tangent and secant because they both have the same denominator. So tangent of z and secant of z are going to be analytic on, what domain? Well, it's just going to be c minus the set of points where cosine is equal to 0, which was pi over 2 plus n pi, where n was an integer, and the points pi over 2 plus n pi. So those are sort of isolated zeros in the denominator, so those will be singularities, according to our definition of singularity. Remember, a singularity is just a point where the function is not differentiable, but there are lots of nearby differentiable points. In fact, the whole deleted neighborhood of all those points, if you take a small deleted neighborhood of all those singularities, it's differentiable on that whole deleted neighborhood. And then cotangent and cosecant are going to be analytic on the places where sine, except for the places where sine is equal to 0, and we saw in the previous theorem. So those are just the places n times pi. So if you exclude those points from their domains, and then those points n times pi are the singularities of those functions. And of course, you can verify for yourself just using ordinary differentiation rules that the derivative of tangent is secant squared, derivative of cotangent is negative cosecant squared, derivative of secant is secant tangent, and the derivative of cosecant is negative cosecant cotangent. So to get all of these rules, you would just put the functions in terms of sine and cosine and then use ordinary differentiation rules to differentiate them. And we know what the derivatives of sine and cosine are, so we can do that. Okay, I think I'll stop there, and we'll finish up this chapter by talking about hyperbolic functions, and then finally inverse trigonometric functions. We'll finish out the sort of standard functions that you need to know about so that you can do calculus with complex functions. Okay, talk to you later. Bye.